Your computer may be doing one piece of work at a time, even when the processor can handle 8, 16, or more. Not because the hardware is slow, not because the task is unusually difficult, but because much of our software still gives the processor work in the most obvious way, one value, then the next, then the next. There is another way. It is called SIMD. The idea has existed for decades. It is already inside modern processors, and in the right loop it can produce a speedup that looks less like an optimization and more like a hardware upgrade. So why do so many programmers treat it like forbidden magic? This week, developer Mitchell Hashimoto published an article with a deliberately broad title, "Everyone Should Know SIMD." His argument is not that every developer should become a processor specialist. It is almost the opposite. SIMD has acquired a reputation for being so complicated that ordinary programmers stop before learning the basic pattern. Hashimoto argues that the common version is much simpler than its reputation. SIMD stands for single instruction, multiple data. A normal or scalar loop might inspect one byte, compare one number, or transform one pixel during each step. SIMD groups several values into a vector and applies the same operation across all of them. One instruction, multiple pieces of data. Imagine a grocery checkout with one scanner. A scalar loop scans 8 items one after another. SIMD is closer to a scanner wide enough to read 8 items in one pass, as long as every item needs the same kind of operation. That last condition matters. SIMD is powerful when the data is regular and the work repeats. Suppose software needs to search a long stream of bytes for a particular value. The straightforward version starts at the beginning and asks the same question repeatedly. Is this the byte? Is this the byte? Is this the byte? A vector version loads a group of bytes and asks the question across the entire group at once. Depending on the processor and the type of data, that group may contain 4, 8, 16, or many more values. The theoretical gain maps directly to the number of lanes in the vector, although real programs also spend time loading data, handling results, and doing surrounding work. Hashimoto demonstrates the pattern with code from Ghostty, his terminal emulator. The program scans decoded characters until it reaches a control character. The original loop checks one code point at a time. The vector version checks groups. He reports throughput improvements of up to 4 times with ARM Neon, 8 times with a VX2, and 16 times with a VX512 for the loop itself. On a VX2 Intel desktop, the broader real-world path improved by roughly 5 times. 5 times from changing how the software asks hardware to perform work. That is the detail that makes this more than a programming tutorial. We often talk about performance as something purchased, a newer processor, a more expensive server, another cloud instance. SIMD is a reminder that performance can also be unused capacity. Hashimoto reduces everyday SIMD to 5 recurring moves. First, prepare the vector and copy, or broadcast, any constant value into every lane. Second, move through the input one full vector at a time. Third, perform the comparison or calculation across all lanes in parallel. Fourth, combine, store, or otherwise interpret the vector result. And fifth, return to an ordinary scalar loop for the small remainder that did not fit into a complete vector. That remainder is called the scalar tail. The terminology sounds technical. The structure is not. Take a repeated loop, divide the input into equal width groups, perform the same work across each group, then clean up whatever remains. The difficult part is often the fourth step, converting a group of results into the exact answer the original program needs. But the surrounding shape remains surprisingly consistent. There is an obvious question. Shouldn't the compiler recognize the loop and do this automatically? Sometimes it does. Modern compilers can auto-vectorize simple arithmetic loops, especially when the data access is predictable and each iteration is independent. That is why measuring optimized scalar code should come before manually replacing it. But compilers must prove that transforming the loop will preserve its behavior. Aliasing, branches, dependencies between iterations, uncertain memory access, and early exits can all block that proof. Even small code changes, or a different compiler version, can change whether vectorization happens. For performance-critical work, explicit SIMD can make the behavior visible and predictable. The programmer is no longer hoping that an optimization appeared somewhere inside the build. The vector operation is part of the program's design. SIMD is not a universal speed button. It is rarely worth the complexity for a loop that touches only a handful of values. It is a poor match when every element requires different logic, when the data is scattered unpredictably through memory, or when the program is already waiting on something slower than the processor. And a theoretical 8-lane operation does not make the complete application 8 times faster. Data movement, setup, reduction, and unrelated work remain. The useful question is narrower. Is this a hot loop, scanning, comparing, counting, or transforming a large amount of contiguous data in the same way? If the answer is yes, developers should at least recognize SIMD as an option. This pattern appears far beyond scientific computing. Image filters repeat calculations across pixels. Audio software processes streams of samples. Databases scan columns. Parsers inspect bytes. Machine learning systems perform enormous quantities of repeated arithmetic. Text software searches, validates, and transforms characters. Libraries such as SIMD-JSON and SIMD-UTF show the extreme end of what vector techniques can accomplish. Their internals can be genuinely difficult, but that complexity should not define the entire subject. The larger issue may be language design. Hashimoto uses Zig because it exposes generic vector concepts without forcing the programmer to write assembly or commit the entire implementation to one processor family. Better language support could let more developers express the idea directly. These values form a group, and this operation applies to every lane. If languages make that pattern ordinary, SIMD stops looking like a bag of processor-specific tricks. It becomes another way to write a loop. The most interesting performance story is not always the next chip. Sometimes it is the capability the current chip already has, and the software never asks it to use. Everyone should know SIMD is deliberately provocative, but its standard is reasonable. Developers do not need to memorize every instruction set. They should know how to spot repetitive work, understand the vector-shaped alternative, and measure whether it helps. Because a 5 times improvement, hiding inside 12 additional lines of code, is not merely an optimization. It is a reminder that faster software can begin with seeing the machine differently. This is SignalShift AI. We explain what changed, why it matters, and what comes next.